So this lecture is on Chapter 5 in your textbook on stereochemistry. I'd like to emphasize here that you should use your model kits and make some of these molecules so that you understand stereochemistry. It's really important. So let me start with chirality. So if we look at your right hand and you take a mirror image of it, it will produce your left hand. And your right hand glove doesn't fit your left hand. So your right hand is essentially chiral because it's essentially different from the original. The mirror image, which is your left hand, is different from the original object. So chirality are molecules that have this handedness. If you take a mirror image of a molecule or of an object, and that mirror images can be superimposed with the original object, that means that molecule is achiral. So a chair would be an example of an achiral entity. It's because its mirror image is essentially superimposable. Stereoisomers are molecules that exhibit a stereocenter in which there's chirality or a handedness. And we'll talk about that in a little bit more detail. In terms about under stereoisomers, you can have what are known as enantiomers. These are compounds that are non-superimposable mirror images, and any molecule that is chiral must have an enantiomer. So here's a chiral molecule shown here. This has 4 different things attached to the center carbon. As a result, it has a star on it, which denotes its chirality. If you take a mirror image, those 4 different things are surrounding that carbon doesn't allow it to be superimposable. This mirror image of a chiral molecule is called enantiomer. Again, like I said in the very beginning, stereochemistry is really difficult for many students, even me, as I was learning organic chemistry. So I can't stress this enough to use your models to help you see the relationship between the structures and understand stereochemistry, enantiomers, etc. that we're discussing here. You can also, if things go by very quickly, you can also pause this video so that you can rewind it and relearn it and understand it at your own pace. So chiral carbon atom, also known as asymmetric carbon, is an atom, a carbon atom that is bonded to 4 different groups. So 1, 2, 3, 4 shown here. Again, a mirror image of a chiral compound. This would be an enantiomer because this is not superimposable and it still has the 4 different things attached to it. Stereocenters, an asymmetric carbon atom is the most common example of what is called a chirality center. Chirality centers belong to a broader group called stereocenters. A stereocenter or a stereogenic atom is any atom at which the interchange of 2 groups gives a stereoisomer. Asymmetric carbons and double bonded carbons in cis-trans isomers are the most common types of stereocenters, and we'll show that example in the next in this slide. So here are stereocenters. All of these are stereocenters that are circled. Here is a stereocenter that's a cis isomer. Here are chirality centers. So a subset of stereocenters that we're focusing on here are chirality centers shown by the star. Now, I've said that carbon is the most conventional form of stereocenter that has been shown, where you can have 4 different groups attached to it. So this is a chiral center or stereogenic center. In the case here, here's a nitrogen. Nitrogen can also have chiral center, as shown denoted by that asterisk star, and because it has 4 different things attached to it, and as a result, it has a chirality center. So asymmetric carbon atoms are examples of chirality centers, which are examples of stereocenters in general. Achiral compounds. So if you take a molecule and you take its mirror image and you find that its mirror image is superimposable, as the example I'd shown you in the chair, that means the compound is achiral. So, this molecule that's the mirror image, if you rotate it 180 degrees, it's an exact identical molecule as the original. So how can you detect achiral molecules? Well, one easy way to do so is to see whether the molecule itself has a plane of symmetry. So here there are, at this same molecule as I shown before, if you view it from this angle, you see that there's a plane of symmetry, if you look at it that way, where these are identical and you have this symmetry. As a result of this plane of symmetry, this molecule is achiral. If we look at cis-cyclic compounds, cis-1,2-dichlorocyclohexane is achiral because it has this internal plane of symmetry right in between. You have this side and this side are equal. As a result, if you take a mirror image of this molecule is superimposable. As a result, achiral. Trans-cyclic compounds, however, do not have this plane of symmetry, right, because they're in trans. As a result, this trans-1,2-dichlorocyclohexane, if you take a mirror image of them, it's not superimposable. As a result, they're enantiomers. Now, in determining configuration of this chiral carbon center, shown here, this is natural alanine versus unnatural alanine. Both enantiomers of alanine receive the same exact name in terms of IUPAC. So if you were to determine this via IUPAC, it would be 2-aminopropanoic acid. This and this are, in terms of naming, are identical. However, one enantiomer, which is this one, the natural alanine, is the one that can be metabolized by enzymes in the body, versus this, the unnatural alanine. So there's a need, there's a need for us to be able to distinguish between them. So how can we do that? Well, Kahn-Ingold-Prelog came up with a convention by which you can actually assign a configuration for asymmetric carbons. And so enantiomers, going back to that example of the alanine, have different spatial arrangements of the 4 group of carbons attached to the asymmetric carbon. There are 2 possible spatial arrangements, and we call them configurations. Each asymmetric carbon atom is assigned a letter R or S based on its 3-dimensional configuration, and we'll talk about that assignment. And it's based on this Kahn-Ingold-Prelog convention to name that R or S configuration. So in order to do so, the first step is to assign the priority. You want to assign the relative priority to each group bonded to the asymmetric carbon. For example, group 1 would have the highest priority, followed by group 2, followed by group 3 and 4. Atoms with the higher atomic numbers receive the highest priorities, and you have to embed this in your memory so that you memorize this. So this is the priority in terms of which takes the priority. Iodine is the highest in priority, followed by bromine, chlorine, sulfur, etc., in this order. So let us assign priorities for this molecules. This is a stereocenter carbon, chiral center, in which they have 4 different things attached to it. Priority will go 1 for the fluorine, NH2, CH3, and then H. And that's based on atomic number as well as that ordering that I had shown you before. Now, there can be cases when you're assigning priorities where you have a tie. So in cases of ties, you use the next atom along the chain of each group as tiebreakers. So here is an example where you have this R attached to CH2, CH2, CH3. When we compare it, for example, to this, which molecule has the higher priority? This does, because this carbon is attached to one carbon and another carbon and a hydrogen, whereas this carbon is attached to 2 hydrogens and then another carbon. So this will take priority. If we compare this to this carbon is attached to 3 carbon atoms, whereas this is only attached to 2. As a result, this will take priority. Now, when we get to adding other heteroatoms like chlorine, so chlorines are going to be have the priority in terms of priority. And so this, even though this has 3 different things attached to it, this has 2 chlorines attached to it. As a result, this will take priority. And then bromine has a higher atomic number. As a result, this will take priority over the chlorines that's being attached. As a result, this will have the highest priority. If you have multiple bonds, you want to treat double and triple bonds as if they were a bond to a separate atom. So as an example, here's this double bond alkene, in which this carbon is attached not only to the R group H and the carbon, but because it's in a double bonded to a carbon, you can say it's attached to another carbon. And this attached to a hydrogen, hydrogen, and a carbon, and because it's double bonded, it's attached to a carbon, and so this becomes this. Same goes with the C double bond N. In this case, this carbon is attached to a nitrogen as well as being attached to that nitrogen, and this nitrogen is being attached to a carbon. Triple bonds, now you have, in addition to that single bond, another carbon being attached and another carbon being attached. Same goes here. And this carboxylic acid, this carbon is attached to an oxygen in addition to that oxygen, and that oxygen is attached to a carbon. Now the second step is to actually rotate the molecule such that the lowest priority is in the back. So again, if we look at this molecule, the lowest priority 4 should be rotated so that it's in the back. And then once you rotate it in the back, you then count the priorities from 1 to 4, or at least 1 to 3 because 4 is in the back. And when you count them, this is going in the clockwise orientation. As a result, this is going to be designated as the R enantiomer. You can do the same with this, where you rotate again this 4 to the back. Now your priorities are 1, 2, 3. It's going in the counterclockwise direction, and as a result, it is given an S configuration. So if we assign the priorities and go back to this alanine, the natural alanine, again it's 1, 2, 3, 4. You're going to push that to the back. This is already showing that it's dashed. The dashed means that it's going to the back of the board. The hash means it's coming out of the page. As a result, you can put that to the back and you can look at the orientation. It's going from 1, 2, 3. That's going in the left or counterclockwise direction. As a result, its configuration is S. So here's another example in which you have a carbon with 4 different things. The priority now is 1 being the hydroxide, this being a longer alkyl chain than this, 3, and this is the last priority. So again, this is now coming to the front, so you want to rotate this so this goes to the back. Once you rotate this so that it goes to the back, this then comes up, right? Hydrogen goes to the back, this goes up, and this comes down out in the front. Once you do that, it's in the back of the board. You're going to now look at what the priorities are, 1, 2, 3. It's going in the clockwise direction. As a result, configuration is assigned R. So it's really important that you use models and you understand this well, because when we're in the class, I'm going to be asking you questions and asking you to assign R and S stereochemistry, so be prepared. Shown here, where we actually rotated, we could have just said, okay, let's count the priority with this in the front, would be 1, 2, 3. 1, 2, 3. 1, 2, 3 is going in the counterclockwise directions, and because it's not facing the back, we'll say, okay, counterclockwise, we'll do it backwards, that will be R. Okay, in general, what I'd like to note is if the lowest priority atom, which is usually H, is oriented towards you, you don't need to turn the structure around. You can leave it as is with the H towards you and apply the R and S rules backwards. So rather than what we had. Okay, now let's move forward. So that's the example that's given, in which you have this molecule. You have a molecule with 4 different things around it. The priority is 1, right? 2, 3, 4. The hydrogen is already in the back. It's going to go in the counterclockwise direction. As a result, it's designated as S. So let's go and do a problem. So draw the enantiomers of 1,3-dibromobutane and label them as R and S. Making a model is helpful for this type of problem, and I urge you to do so. You can pause this and do it, and then see if you get the solution right. So the third carbon in atom in the 1,3-dibromobutane is asymmetric, which is over here. So then we can draw this in terms of line structures with the hash marks going to the back and the wedge marks coming out. So the bromine receives first priority. The CH2, CH2Br second, methyl third, and the hydrogen fourth. So if we draw this out, we're going to see that, I'm sorry, this is showing alanine and unnatural alanine. So yeah, so this shouldn't be alanine and unnatural alanine. It should be bromine, ethyl bromine, and methyl. So you can draw this out, and I'll do this in class. And you have a hydrogen that's going to be 4. You have your bromine group, which is going to be 1. So instead of the NH2, we can put the bromine group here. The second group would be CH2, CH2Br here. And the third group would be CH3. This would be the S. And then you can do the same thing here and switch it around so that the first group is Br, second group is CH2, CH2Br, methyl group H in the back. This is clockwise. So yeah, I apologize for this not showing the right actual molecule, but if you can just substitute those and do it on your own, that would be good. So if we look at configurations in cyclic compounds, so here's S-carvone. You can determine the chirality of it as S by first prioritizing what groups 1, 2, and 3 are. So 4 is definitely going to be the H. 1 is going to be this compound because it has carbon attached to multiple carbons, right? Here 2 is carbons attached to hydrogen, but if we go down this line, this carbon is now attached to oxygens, whereas this is just carbon is attached to carbons. And so if we do them out from that stereocenter, carbon group 2, CH2, C, right, O, because of the double bonded O, which is attached over here, and this C as well as here, down below. Group 3 would be carbon, CH2C, right? So we're looking at here and here, CH2C. Then C is double bonded to another carbon here with CH3, and then the ketone group over here. So that's how we assign priorities. 1, 2, 3. This is going in the counterclockwise direction. The H is pointed towards the back. As a result, is S. Properties of enantiomers that are important. They have same boiling points, melting points, and density. They have the same refractive index. They rotate the plane of polarized light in the same magnitude, however, in opposite directions. And that's the key with enantiomers. So they have same properties except for the plane of polarized light. They also have different interactions with other chiral molecules. For example, active sites of enzymes are selected for particular enantiomers. Taste buds and sense receptors are also chiral, and enantiomers may have different. So polarized light. Plain polarized light is composed of waves that vibrate only in a single plane. So if we take a light source, the light source always are vibrating in all different directions. If you put it through a polarizer, it'll generate plain polarized light, so it's only generating waves that are vibrating in a single plane. So in terms of optical activity, an enantiomer rotates the plane of polarized light in opposite directions, but the same number of degrees. So if we take our light source, here's our filter, monochromator filter, but then you put a polarizer, you'll now get one plain polarized light. If you put it through a sample that has a particular enantiomer, it will rotate that. So you're seeing that the light is being rotated a certain degrees that you can detect. So when you take this setup is in a polarimeter. If it's to the positive, if the plane polarized light is changed to the positive direction, it's dextrorotatory. If it's to the negative direction, it's levorotatory, and this is not important, not related to the RNS. So a lot of students always confuse S with minus, R with plus, and they make that association, but that's not the case. Your R's could have a negative levorotatory signal, and your S could have a dextrorotatory signal. Specific rotation. So the observed rotation depends on the length of the cell and the concentration, as well as the strength of the optical activity, temperature, and wavelength of light. So here's the equation that you're going to need to know and memorize, where the A observed is the rotation observed by the polarimeter. C is the concentration in grams per milliliters. L is the length of the sample in decimeters. And so this will give you the specific rotation. So let's do a problem. When one of the enantiomers of 2-butanol is placed in a polarimeter, the observed rotation is 4.05 degrees counterclockwise. The solution was made by diluting 6 grams of 2-butanol in a total of 40 mils, and the solution was placed in a 200 millimeter polarimeter tube for measurement. Determine the specific rotation for this enantiomer of 2-butanol. Since it's levorotatory, it's going to be negative, right? So the concentration of 6 grams per 40 mil is 0.15 grams per milliliters. Path length is, you're going to convert the millimeters into decimeters, so it's 2 decimeters. So the specific rotation is going to be this minus 4.05 divided by 0.15 and times 2. Here is your answer. In terms of biology, like I've said, certain enantiomers are recognized by certain enzymes. So, for example, the R epinephrine, which is the natural epinephrine, is recognized by the enzyme in a particular way because of its configuration. So this allows just the R to be recognized versus the S doesn't provide the right configuration and cannot fit the enzyme. And so I'm going to stop here for the first half and continue on later.